groups. Time to learn. We're going to look at energy transfers in SHM, and we're going to print in this color today. Energy transfers during SHM. So we'll use our famous bob, okay, our oscillating bob, and essentially what we'll say is our object, our mass, is set on springs between two posts, and it oscillates back and forth like this. Okay? Okay, so just for fun, we'll put in our fun little Wikipedia oscillator here. So this goes into what we were talking about last time, the relationship between displacement. You know, if you want to say the blue line here is following our oscillating bob back and forth this way, well then if that's displacement, then the velocity is going to be related like that. And the acceleration is going to be the inverse of our displacement graph. Okay? I kind of covered that before. But now what I want to talk about is what goes on with energy. Okay? So I'm just going to take that, I'm going to turn it on its side. All right? Oops. I'm going to take that picture, I'm going to turn it on its side. We're going to just think about what this thing is doing as it bounces. Okay? So there, we'll put it there. Here, 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 and here. So these represent like separate points in time of this thing oscillating. I'll draw on my springs real quick. It sounds like something they'd say in the South. Let's do this real quick. Okay, I'll put this here and that there. Okay, so if we call this the neutral position, all right, and we call this our maximum displacement x, and this our minimum or our most negative displacement x, all right. Another word for this is the amplitude, right, it's a measure from our neutral position. And we think about what the bob would be doing at these different times. When it's here, you got a max velocity, and we've covered this before. So v is max here. It's min here. Okay. It's negative max here, right? It's min here. It's negative min here. Negative min here. And it's max here, max positive. So if we want to talk about energy, right? I want to talk about energy. We've got essentially an interchange of types of energy. So we have EK, which if you remember is found as 1/2 mv squared. So in other words, it's in this case, since mass is set by the size of this, it is proportional to the square of the velocity that you have here. All right, so it's highest here. Okay. The other thing to think about is when your velocity drops to 0, so does your EK, right? Your EK at this point is 0. But if we say that this is a system that doesn't leak energy, right? This is a system, a perfect system, then we must be storing that kinetic energy somewhere, and it's stored in terms of spring potential. So here we have a max EK. Okay. Here we have a max spring potential energy, so EE is equal to 1/2 kx squared, so it's proportional to the distance away. Okay. Then we're back to EK here being maxed, and then we're back to all of our energy stored in the spring when this has stopped moving. So again, EE equals 1/2 kx squared, and then we're back to maximum EK. So the first question is, can you have negative potential energy? Can it be negative? You can have negative work. That means you're working against the direction of travel, right? But it still requires energy to do negative work, and it requires energy to do positive work. Can work itself, or sorry, can energy itself be negative or positive? Does it make any kind of like intuitive sense that you could ever have negative energy. What was our definition of energy? The stored ability, or the ability to work. Right? That's all it is. It's the ability to work. Okay? Could net energy be if you don't have any energy, you can't do work, right? It's not like you can somehow do negative work by having negative energy. So what I'm trying to get at here is you're going to have a graph that has no negative values on it, right? You're going to have an interchange between two types of energy, but the baseline is going to be 0, right? So it's not quite the same as looking at the relationships between velocity and acceleration and displacement, okay? It's going to be a little bit different. So let's see if we can graph out how we think that's going to look. How can we make sense of what's going to happen here? So we have this. Now, this system contains some certain maximum amount of energy, right? And that maximum energy is equal to EK here, and it's equal to EE here. Or it's equal to the sum of both in between, right? If we go here, a little bit off of neutral, say on our way up, we have, or I guess it would be back here, we have lost some of our kinetic energy, but we've gained it as spring potential, right? So on our way up, kinetic energy drops and spring potential goes up, right? And then the opposite thing happens. As we go down, kinetic energy increases, spring drops, spring 0, kinetic energy is maxed, and now kinetic starts to drop and spring starts to go up, and so on, okay? The sum of all of this will equal to whatever energy this system has, okay? The total energy of the system. So let's call that E total. What is E total? Well, E total, this, is equal to the EK plus the EE. Sometimes the elastic or spring potential energy is 0, right? Sometimes it's a little bit in each of these, and sometimes it's the other way. But this is set by the system, okay? So let's say that EK is in this nice bright green, okay? Right at the beginning here, when we're at our neutral position, EK is at its max, right? EK is at its max. You with me? Spring potential, which we have in blue, is at its min, at its minimum. That's like right there. Then by the time we get to the maximum height here, we've dropped our we dropped our EK to nothing, but our spring potential is now maxed. Right? Spring potential is now maxed. This has dropped down to nothing. Okay? Then by the time we get here, we're now on our way back down, and remember, we can't have a negative energy. This makes sense. So now we're back to whipping as fast as we can go. So our kinetic energy is now back up to maximum right here. Okay, should have drawn these a little more evenly spaced. Let's move this over a little bit. Erase this guy. Okay, and our spring potential energy, right, as we go past the neutral spot, is now down to nothing. Okay, now we're down here. Spring potential is maxed again. Kinetic energy is min, and here on our way back up through to complete our single oscillation, right, our kinetic energy is back up to max, and our spring potential is now down to 0. So in one oscillation, we have this for energy changes. It's not quite as even as I would have liked. It should be. So if you look here, right, if you look, we have essentially double the frequency that you had for the actual frequency of the object. So the energy changes happen at double the frequency. So again, the green line represents what our kinetic energy is doing. The white or blue line represents what our spring potential energy is doing. So for one oscillation of our spring pendulum, we actually have 2 complete flip-floppings in terms of what the energy is doing. Okay? We don't really need to get crazy. We don't have to derive any equations for that. We just need to be aware that that's what's happening, okay? So the frequency of energy changes is twice the frequency that the object is bobbing at. So one last thing just to say here is that the sum of these will always equal the orange line that we drew, right? So I don't know, if we make this 0.5 and we make this 1, at this point 0.5 comes from spring and 0.5 comes from kinetic. Here, okay, none comes from kinetic, all comes from spring. So at that point we must be at one of our extremes, and there we are, okay? And really that's all I have to say about this.